consider changing the speed to 1.25 and turning the captions on. Enjoy! Hi, I'm Errichto, and in this lecture I will tell you about dynamic programming, what it is, some example problems like staircase, Fibonacci and minimum path in a grid, and we'll compare recursive and iterative methods and choose the better one. In the following lectures we'll see harder examples and techniques in dynamic programming. Dynamic programming, or in short DP, is about finding some work that the naive, usually recursive, solution would repeat multiple times unnecessarily. Instead, it's better to save the result of that sub-problem and reuse it multiple times to avoid extra computation. Most of dynamic programming problems belong to one of three types or categories. The first of them is to count something, like the number of ways to rearrange elements in a sequence to satisfy some condition, or the number of paths from one vertex to the other. The second type is to optimize certain value or quantity, and the third one is to check if something is possible. For example, given a set of numbers, check if there is a subset with the sum of elements equal to exactly the target value that is given. For second and third types, you should sometimes think whether maybe a greedy, easier approach is possible. Those are sometimes similar to each other, dynamic programming and greedy, like in Cadence algorithm. It's actually hard to tell whether Cadence algorithm for maximum subarray is greedy or DP. Before solving problems, let's compare the iterative and recursive method to approach dynamic programming. Iteration is usually about writing a few for loops that are nested inside each other. The advantages of this method are speed of a program, the overhead is smaller and thus the running time is smaller. Code is shorter and cleaner usually, and thus it's easier to say what is the time and space complexity of a program. And finally, in hard problems, sometimes iteration allows us to apply harder techniques like prefix sums and segment trees. On the other hand, recursion is easier because we can implement a naive solution or backtrack and then just add memoization. So it's easier to apply recursive dynamic programming to a problem. In some single problems, the number of states we will visit is smaller and the complexity might be even better, but that's not often the case. And finally, the order of states doesn't matter. In recursion, we don't have to care about the order of states, while in iteration, we need to decide about it. It's hard, for example, in graphs. If we are given a DAG, directed acyclic graph, we need to first apply topological sort to be able to run iteratively through vertices later and apply dynamic programming. That being said, especially because of smaller running time and being able to apply harder techniques, I strongly prefer iterative dynamic programming, and this is what most people do in competitive programming as well, among top participants. So let's stick with iterative. Our first example is the Fibonacci series, a sequence where the first two elements are 0 and 1, and then every next element is the sum of two previous elements. F of I is f of I minus 1 plus f of I minus 2. We can implement a function that will recursively run itself. F of given I will sum up f of I minus 1 plus f of I minus 2. Except for I equal to 0 or 1, then we know the answer immediately. If we run that for, let's say, f of 5 to compute the fifth Fibonacci number, it will run f of 4 and 3, then f of 4 will run f of 3 and 2, and already we ran f of 3 two times. Some computations will be repeated unnecessarily. Let's see the whole tree that shows us what are the calls. At the top we see the first run, f of 5, that needs f of 4 and f of 3 to be computed. Then f of 4 runs f of 3 here, and let's say after all the subtree is done, we have some value here, some x. Then much later, when we are on the right, f of 3, we don't have to go below. This is what is called a repeated subproblem. We don't need to run that recursively, we just know that this is already that x that we can save. Same thing for f of 2. Instead of computing that again, running recursively, if here we had a value y, then the same value should be here, y. This way our tree from the size, from exponential size, will become actually linear. Let's see the implementation to make that more clear. Now for a moment you see the recursive solution with memoization added. If you want to, you can stop a video and read it, but we want to focus on the iterative version that is here. We create an array f, we fill two first elements, f of 0 and 1, that's often called base case, and then we compute every next element using previous ones. Because n Fibonacci number needs values of n-2 and n-first Fibonacci numbers, those need previous numbers and so on, we anyway need to compute all the values up to n. This is why we just iterate through them and compute each of them in constant time using two previous values. The order that we go from I equal to 2 to n is very important in iterative dynamic programming. Sometimes it's not that trivial, but once the order is chosen and some array, some state, here state is just I, f of I is the I Fibonacci number, then we apply transition that somehow we get from the statement. This time it was very easy because we were given a formula. In next problems it won't be that easy. Another bonus here is to solve the problem in constant time. If you have first and second Fibonacci number, you can use them to compute third one, and then you can forget about the first value. You can iterate and only remember the value of two consecutive Fibonacci numbers, use them to compute the next one, and forget the ith number, and only move to I plus 1 and I plus 2. This way, just with two variables, and then choosing extra third variable, you can solve the problem in constant space, what is often a question in some contests or coding interviews. Let's see that dynamic programming isn't always necessary in those problems where we are given a formula. One example of that is a factorial. Factorial of I is defined as factorial of I minus 1 times I. If you draw a tree that shows what a recursive function will call, f of 5 will call f of 4 and so on, there isn't any repeated work, and this means that dynamic programming isn't necessary. Still, you can create an array, and f of I you can compute as f of I minus 1 times I. It's actually useful if you want to remember all the factorials and then be able to answer for the I factorial in constant time. But if you just want to compute one, then a for loop is enough, or a recursive function. Both will be just linear and dp isn't necessary. There are two examples left, and in them I will show you how I think about a dynamic programming problem and how I approach choosing a state and transitions. First, problem stairs. You're climbing stairs, it takes n steps to reach to the top. Each time you can either climb 1 or 2 steps. Count distinct ways you can climb to the top. And there's an example with 4 steps to climb, and one of those ways is to first climb 1 step, then 2, then 1 again. This path is one of multiple possible paths, and we should count them. If n is huge, then this problem would tell us to print the answer modulo some value, otherwise it will be huge. When we are at some step, let's say here, it doesn't matter how we got here. Maybe we took single steps, maybe it was first 2 steps, then 1 step. It doesn't matter, because the problem doesn't tell us, for example, that 2 consecutive steps can't be of size 2, something like that. It only matters where we are. This is why the state must be just a position, I, or pos like position, and this suggests the dimension of dp should be that I, position. Because the problem tells us to count ways, I will define that as integer int dp of I. That means the number of ways to get here. If the problem asks me to compute the minimum number of jumps to make something, then that would be the minimum number of jumps. If the problem asks me, is it possible, then this would be just a Boolean value that says whether I can get here, yes or no, true or false. If we need to maximize something, that would be maximum value that we need to maximize to get here. If we define the state as int dp of I, the number of ways to get here, then we have an easy transition, because we know to I we can get to from I minus 1 or I minus 2, then the transition is dp of I is dp of I minus 1 plus dp of I minus 2. You can see here similarity to the Fibonacci sequence, and actually it's the same thing. The story is different, but the problem is exactly the same, and the answer will be the same. Maybe to n you should add or subtract 1, because the base case might be different. Here the number of ways to get to 0th step is 1. This is just an empty path. Then to the next one is 1, and every next step the number of ways is the sum of two previous values. Here the answer would be 5. But what if the problem is more complicated? What if we're additionally we're given value k, and the statement said at most k jumps, or well, moves you make. At most k jumps. Then when you're at some position I, you can't anymore say it doesn't matter how you got here. There are exponentially many ways you got here, but what is important is the number of jumps you made. There is a difference if you are here, whether you made 1 jump, 2 or 3, or maybe 0 if that's possible. This means we should add that as a dimension of dp. The state isn't just described as position, it's also the number of jumps to get here. Then I change that to dp of I and let's say lowercase k. That means the number of jumps to that position. At the end, instead of just printing dp of n, the number of ways to get to the nth step, we'll print the sum over, the answer will be the sum over dp of n and j, the number of jumps, over j from 0 up to k, because we are allowed to make at most k jumps. It's easy after that define to see the complexity as well. The space complexity is O of n times k given in the input. Those are 2 dimensions. And every state you compute in constant time. dp of I k is dp of I minus 1 or minus 2 of k minus 1. To that previous step, you made the number of jumps smaller by 1. And this is exactly how I approach dynamic programming problems. I think when we are at some position, what is important so far? Is the number of jumps is important? Maybe the last jump is important because we are forbidden to make 2 same consecutive jumps. Let's see the same thing on the next problem. Minimum path sum. Given a grid, find a path from the top left to the bottom right corner that minimizes the sum of numbers along the path. You can only move right or down each time. For example, given this grid with 3 in the top left corner from which we should start, the optimal path turns out 3, 2, 1, 2, 3, 4. Remember that we said for problems that ask you to optimize some value, not count the number of ways, you should often think about an easier greedy approach. Here, that idea would be to maybe go to that neighbor of yours, starting, let's say, from 3, that is smaller. From 3, maybe greedily we should take to 1, but this example already shows us that It's a bad approach because maybe in a moment we'll have to get to a big number, here a 9. And if greedy doesn't work, then usually dynamic programming is a way to go. We will try the same approach that I told you about for the previous problem. When you're at some position, actually sometimes you can think about it after some time, after some number of steps or seconds, what is important so far. When you are, let's say, at this 2, it doesn't matter whether you visited maybe this 1. It doesn't matter what exactly is your path, other than the score so far, the sum of values. Here it would be 3, 2, 1, and 2. And this is why I would say dp of that row and column, because this is the position, is in that case it would be what, 5, 3, 8. Int dp of row col is the minimum sum so far, minimum because the problem asks us to minimize the sum of numbers along the path, minimum sum of numbers so far up to this moment. And the end, we will just print this value dp in that position as the answer. As with previous problems, transitions are very easy, because when you are at some cell, row col, you know that previously you had to be in one of cells to the left or to the top. You need to take the maximum of those values dp plus the value in this new cell, because you extend a path by 1. If this problem told you, for example, that you cannot make 2 consecutive steps down, then you can't anymore say the only thing that matters so far is the sum of values, but also the previous step. So for a problem where you can't make 2 consecutive steps down, the dp would be row, column, and here 0 or 1 for the previous step, whether it was right or down. If that previous step is down, then the new one can't be. One more thing that we'll talk for future lectures is forward versus pull from previous dp. Here dp of row col we can compute as the maximum of 2 previous numbers, or alternatively we could use already computed dp of row col for some cell to update the potential best dp value in the next 2 cells, one to the right and one that is down. Later we'll see examples of problems where that other method is better and easier to apply. Today we compared iterative with recursive approaches, and I told you why I prefer the iterative version in general. The main part of the dynamic programming is to say, when we are at some position, what is important to remember so far, not exactly the shape of a path that we went till this position, but the sum of elements that we need to minimize, or the last step or the number of steps that is required to move forward, because the problem tells us some limit for the number of steps. Finally, you can go through problems we talked about and make sure you understand what base case to put there, so how to initialize the array. If you want to minimize something and you need to fill all the values in the array, then maybe infinity is a good idea, and just put 0 in the very first cell. Otherwise, if zeros are everywhere and you need to minimize something, there will be still minima everywhere. Plus, transitions usually come from the statement. In those problems that we talked about, it was quite easy to see that to some cell you can get from to neighboring cell, to previous cells. In the next lecture we'll see obviously harder examples, and finally, either in the next lecture or in some videos, I will again go through AdCoder dynamic programming contest problems, at least first 6 problems, and there we'll apply multiple not so easy techniques. Right now, I want to thank you for watching and see you in the next dynamic programming lecture. Bye bye!